All right, welcome to the deep dive. Today we're going deep, really deep, into something I know a philosophical mind like yours will find inherently fascinating.
Oh, do tell. I'm intrigued already.
We're diving into proof theory, the bedrock of how we actually establish truth, especially in logic and mathematics.
Ah, proof theory. Yes, that's a rich area full of deep philosophical implications.
Exactly. I think it's going to give you a really insightful perspective on things you're already familiar with, like what even is a proof? What does deduction really mean? Those sorts of fundamental questions.
Absolutely. I'm always up for revisiting the foundations of knowledge.
So to guide us on this journey, we're going to be drawing from the Stanford Encyclopedia of Philosophy's entry on, well, the development of proof theory.
A classic. It's a comprehensive overview, really authoritative. A perfect guide for our deep dive.
And our mission today, well, it's to unpack the key moments, the big ideas, the turning points in how proof theory evolved. And especially, because you are who you are, I want to pick out the things that really make a philosopher think about, what proof is, what consistency means, and whether there are limits to what we can even systematize, formally.
A grand philosophical quest indeed, exploring the very limits of what we can know and prove.
Exactly. Okay, so to kick things off, let's go way back, like prehistory of proof, back to Aristotle.
Ah, Aristotle. Always a good place to start when talking about logic and knowledge.
Right. Especially his ideas about demonstrative arguments in the Analytica Posteriora.
Right, where he sort of laid out this vision of scientific knowledge as a kind of deductive structure.
Yes. Built on like these fundamental undefined terms, axioms, and then from those you build up, you derive theorems through, rigorous proof.
A powerful idea that has shaped Western thought for centuries.
And what's so interesting, right, is that at the same time, Euclidean geometry was being developed, and that also had this axiomatic structure.
Ah, yes. Euclid's Elements, a model of axiomatic deductive reasoning.
Exactly. And it just makes you think, right? Because here you have this beautiful systematic way of starting with a few basic assumptions and then deducing this whole universe of geometric truths.
A testament to the power of human reasoning.
But, and here's where it gets really interesting, Aristotle's own formal logic, the syllogisms, it seems like that actually had very little to do with how those geometric proofs were constructed for centuries.
You're right. There's this intriguing disconnect. The practice of geometric proof remained, well, largely intuitive for a very long time.
Relying on visual intuition, like things that seem self-evident.
And that contrast between formal logic and the actual practice of mathematical proof, I think that's what set the stage for the later attempts to formalize proof more rigorously.
Yeah, like they saw this gap and thought, we need to make this more precise, more systematic.
Precisely. And that brings us to a pivotal figure, Gottlob Frege, and his groundbreaking work Begriffsschrift in 1879.
Begriffsschrift. I mean, the name itself sounds intimidatingly formal.
It does, doesn't it? But the idea behind it was revolutionary. Frege really wanted to eliminate any reliance on intuition in proofs.
To make every single step explicit.
Exactly. He envisioned this symbolic language so precise, so rigorous, that every inference, every deduction would be completely spelled out, leaving no room for ambiguity or hidden assumptions.
That's a huge philosophical shift, isn't it? Like going from this idea of combining arguments, which Aristotle did, to this concept of a complete finite set of rules for deduction.
Absolutely. And Frege actually managed to achieve this for classical propositional logic. He developed a system of rules that was, well, complete. Every logical truth in propositional logic could be derived using his rules.
That must have been a huge accomplishment, really solidifying the idea that logical truth can be captured purely, formally, syntactically, just by manipulating symbols according to strict rules. It does make you wonder, though, about the status of intuition in mathematics. Is there any role left for it, or is mathematical knowledge ultimately reducible to the mechanical application of rules?
A profound question indeed, and one that continues to be debated among philosophers of mathematics to this day.
So we've gone from Aristotle's vision of deductive knowledge to Frege's rigorous formalization of logic. Where do we go from there?
Well, around 1890, we have Giuseppe Peano entering the scene.
Peano. He's famous for his axioms of arithmetic, right?
He is, but his work goes much deeper than that. People often think he just formalized the language of arithmetic, with those axioms.
But she did more.
He did. If you look closely at his work, especially his Arithmetices Principia, you'll see that his proofs are actually purely formal derivations. Each step is meticulously justified using very specific rules.
So he wasn't just giving us symbols to talk about numbers. He was giving us the rules for how to reason about them in a completely formal way.
Exactly. He explicitly stated two fundamental principles of derivation. First, that axioms imply any instance of themselves, and second, modus ponens.
Modus ponens, the classic, if P, then Q, P, therefore Q.
Precisely. So he was really building a formal system for proof in arithmetic.
That's a key distinction, isn't it? He wasn't just creating a language. He was defining the very rules of the game for how to prove things within that language.
Precisely. And his meticulous attention to detail really set the standard for rigor in mathematical proof.
Okay, so we have Frege's formalization of logic, Peano's formalization of arithmetic. What comes next in this grand narrative of formalizing truth?
Well, in the early 20th century, we have Bertrand Russell building upon the work of both Frege and Peano.
Ah, Russell. Famous for his work on logic and the foundations of mathematics.
Yes, and his monumental work, Principia Mathematica, co-authored with Alfred North Whitehead, was a truly ambitious project.
Principia Mathematica. I've heard the name, but I'll admit I've never actually delved into it. It's supposed to be quite dense, isn't it?
It is, but it's a landmark achievement. What they tried to do was to derive the whole of mathematics from a few basic logical axioms.
Wow. So reducing all of math to logic, a truly grand vision.
It was, and they adopted Frege's logic, but importantly, they used Peano's notation and his explicit rules of proof.
So combining the best of both worlds in a sense.
Exactly, and they relied heavily on modus ponens and universal generalization as their fundamental rules of inference.
Universal generalization, that's the idea that if you can prove something holds for an arbitrary object, you can conclude it holds for all objects of that type.
Precisely. It's a powerful principle, and it's crucial for proving general theorems in mathematics.
So you have this Fregean-Russellian vision, this idea that you can ground all of mathematics in pure logic, just a handful of axioms and a couple of inference rules. That must have seemed like a definitive answer to the question of mathematical certainty.
It was a hugely influential idea, but it's also important to note that there was another approach to logic developing at the same time, the algebraic approach pioneered by Boole and Schroeder.
Ah, Boolean algebra. I've heard of that, but it's not really proof theory, is it?
Well, it turns out that Boolean algebra can be seen as a precursor to modern predicate logic. In fact, the Lowenheim-Skolem theorem, which is a key result in proof theory, actually emerged from the algebraic tradition.
So there were these parallel developments happening, but ultimately the Frege-Russell approach won out.
Yes, largely due to the influence of David Hilbert and his emphasis on axiomatic systems and formal proof.
Hilbert, now there's a name that looms large in the history of mathematics. His work really set the stage for modern proof theory, didn't it?
Absolutely. His work on the foundations of geometry in the late 19th century really crystallized a program for foundational research in mathematics.
And he outlined these four key problems, right? The formalization of mathematical theories, proving their consistency, establishing the independence and completeness of their axioms, and solving the decision problem.
Exactly. Those four problems really captured the core challenges of providing a secure foundation for mathematics.
And I think for a philosopher, those questions are deeply resonant. They're about the limits of what we can know and prove, about the nature of truth itself.
They are indeed. And Hilbert, in a way, brought the tools of mathematics itself to bear on these philosophical questions. He advocated for what he called metamathematics, the study of mathematical systems using mathematical methods.
So like using math to analyze math itself.
Precisely. And he had early successes, particularly in the formalization of logic. Propositional logic was shown to be consistent, complete, and decidable. There were also important results for predicate logic, like the Lowenheim-Skolem theorem.
But then came Gödel, and his incompleteness theorems really shook things up.
They did. Gödel showed that any sufficiently powerful formal system, like Peano arithmetic, would inevitably be incomplete. There would always be true statements that could not be proven within the system.
And even worse, he showed that you couldn't prove the consistency of such a system using only the system's own resources.
That's right. It was a devastating blow to Hilbert's program, and it really forced a reevaluation of the very foundations of mathematics.
It's interesting how von Neumann, he independently discovered some of Gödel's results but chose not to publish them because he knew Gödel had already done so.
It shows the remarkable intellectual honesty and generosity of these great minds.
Absolutely. And von Neumann instantly recognized the implications of Gödel's work, even conjecturing the unprovability of consistency for mathematics as a whole. It's like he immediately grasped the profundity of what Gödel had uncovered.
And he wasn't alone. There's that famous anecdote about von Neumann interrupting his lectures to excitedly explain Gödel's findings. You can almost feel the shockwaves going through the intellectual community.
Yeah, like a paradigm shift was happening right before their eyes.
Precisely. The old certainties were crumbling, and a new understanding of the limits of formal systems was emerging.
So Gödel's theorems really cast a shadow over Hilbert's program. But the story doesn't end there, right?
No, it doesn't. In fact, in a way, Gödel's work opened up new avenues of investigation.
Such as?
Well, for example, both Gödel and Gensen independently discovered translations between classical and intuitionistic arithmetic.
Intuitionistic arithmetic, that's a different kind of logic, right? It's more restrictive.
It is. Intuitionistic logic rejects the law of excluded middle, which says that every proposition is either true or false. It demands constructive proofs, where you actually have to exhibit the object whose existence you're claiming.
So it's a more grounded, more concrete kind of reasoning.
It is, and Hilbert had considered it a weaker form of logic. But these translations showed that if classical arithmetic was inconsistent, then intuitionistic arithmetic would be inconsistent as well.
So in a way, they were equally powerful, despite their differences.
Exactly. And this was a bit surprising because intuitionistic logic seemed to be based on more fundamental, more finitary principles.
And Gensen, even before Gödel, had set out to prove the consistency of arithmetic. It was his driving ambition.
It was. And he initially tried to do this using traditional axiomatic methods, focusing on arithmetic with the principle of complete induction.
But those attempts didn't quite pan out, did they?
No, they didn't. He ran into technical difficulties, and it led him to develop a new approach, a new way of looking at the structure of proofs.
And that's where natural deduction comes in, right?
It does. Gensen observed that the way mathematicians actually construct proofs is often quite different from the axiomatic method.
How so?
Well, mathematicians often make temporary assumptions, explore their consequences, and then discharge those assumptions. They break down both the assumptions and the desired conclusion into smaller pieces until they see a logical connection.
It's a more dynamic, more organic process than just starting with axioms and mechanically deriving theorems.
Exactly, and Gensen captured this process in his system of natural deduction.
And the key idea is introduction and elimination rules for each logical connective, right?
Precisely. The introduction rules tell you how to build up a proposition of a certain form, and the elimination rules tell you what you can infer from a proposition of that form.
And you gave the example of conjunction earlier. To prove A and B, you need to prove A and you need to prove B. That's the introduction rule. And if you have A and B, you can infer either A or B. That's the elimination rule.
Exactly. And Gensen showed that you can systematically remove unnecessary detours in proofs, a process he called normalization.
Normalization, making proofs more direct, more efficient.
Exactly. And in normalized proofs, a crucial property holds. The premises of each inference step are always subformulas of the conclusion.
Subformulas solely, smaller pieces of the conclusion.
Right, and this subformula property had important consequences. It led to a decision procedure for intuitionistic propositional logic and a purely syntactic proof of its consistency.
So analyzing the structure of proofs in this way actually yielded results about the consistency of the system.
It did. But when Gensen tried to extend natural deduction to arithmetic, particularly with the rule of mathematical induction, he ran into problems.
Problems? What kind of problems?
Well, the formulas involved in induction could become arbitrarily complex, which messed up the subformula property.
So natural deduction wasn't quite powerful enough to handle full-blown arithmetic.
It wasn't, at least not in its initial form, and that led Gensen to develop his other system, sequent calculus.
Sequent calculus, I remember you mentioning that earlier. It's a different way of representing proofs, right?
It is. In sequent calculus, you have these things called sequents, which are basically lists of formulas separated by a turnstile symbol.
The turnstile, that's like an arrow, right? It means implies.
Exactly. So a sequent like A, B, C means that from the assumptions A and B, you can derive the conclusion C.
And Gensen developed specific rules for manipulating these sequences, rules for each logical connective.
He did. And one of the key innovations was allowing for multiple conclusions on the right-hand side of the sequent.
Multiple conclusions, so like A, B, C.
Exactly. This was crucial for capturing classical logic, where you can have things like the law of excluded middle, which says A or not A.
So sequent calculus was a more general, more powerful framework than natural deduction.
In a way, yes. And Gensen proved his famous Hauptsatz, his main theorem, for sequent calculus.
The Hauptsatz, or as it's more commonly known now, the cut elimination theorem.
Right. The cut rule allows you to introduce an intermediate lemma into a proof, even if that lemma doesn't appear in the final conclusion.
So it's like a shortcut, a way to streamline the proof.
It is. But Gensen's theorem showed that you can always eliminate the cut rule, that any proof using cut can be transformed into an equivalent proof without cut.
So the cut rule is convenient, but ultimately it's not essential.
Exactly. And this has deep implications for the structure of proofs. It means that proofs can be made more direct, more transparent.
It's remarkable how this technical result about the cut rule actually tells us something fundamental about the nature of proof itself.
It does. And it's a testament to the power of Gensen's sequent calculus as a tool for analyzing proofs.
And you mentioned earlier that Gensen had actually proven a normalization theorem for natural deduction, but that proof wasn't widely known for many years.
It was only rediscovered among Paul Bernays' papers much later.
It makes you wonder what other gems might be hidden in the archives, waiting to be unearthed.
It does. The history of logic is full of fascinating twists and turns.
And after developing these powerful tools, natural deduction and sequent calculus, Gensen returned to his original goal, proving the consistency of arithmetic.
He made several attempts, starting as early as 1934, just after finishing his thesis.
And those early attempts, well, they weren't without their problems.
No, they weren't. His first attempt is lost to history, and his second attempt was flawed. It relied on a reduction process for sequence, but the assumptions underlying the proof weren't clear.
And that led to criticism from Gödel and Bernays, right?
It did. They pointed out the gaps in his reasoning, which pushed Gensen to refine his approach.
And that led to his third attempt, the one using transfinite induction.
Yes, in 1936, he published a proof that used transfinite induction up to the first epsilon number, but the paper was quite difficult to follow because he changed the logical calculus midway through.
So even though it was a breakthrough, it wasn't as clear and elegant as it could have been.
Right, and realizing this, Gensen produced yet another proof in 1938.
His fourth attempt, this one was more solidly grounded in his sequent calculus LK, which he had developed back in 1933.
Exactly. And he made the use of transfinite induction much more explicit and transparent.
So even in the face of setbacks and criticism, Gensen just kept refining his approach, pushing the boundaries of what was possible.
He was relentless in his pursuit of a consistency proof for arithmetic.
And ultimately he succeeded, right?
He did. His final consistency proof, published in 1943 but written in 1939, took a different approach. He extended piano arithmetic by adding transfinite ordinals, and then showed that transfinite induction up to the first epsilon number was a statement that could be expressed but not proven within piano arithmetic.
So he found a concrete mathematical principle, transfinite induction, that went beyond the limits of piano arithmetic.
Exactly. It was a different kind of incompleteness result than Gödel's, but equally profound.
And this led to the concept of the proof-theoretic ordinal of a system, a measure of its inductive strength.
It did. Gensen's work marked the beginning of the field of ordinal proof theory, a sophisticated way of analyzing the strength of formal systems.
Yes. And his achievements, though perhaps less widely known than Gödel's, were equally groundbreaking.
They were. He provided a new perspective on the limits of formal systems and the power of inductive reasoning.
And even Gödel recognized the significance of Gensen's work. He developed his dialectica interpretation as a way of responding to Gensen's ideas.
And others, like Ackermann and Kreisel, also built upon Gensen's work, further developing the field of proof theory.
It's amazing how these groundbreaking ideas sparked so much new research and led to entirely new fields of study.
It's a testament to the power of fundamental discoveries to reshape our understanding of the world.
And of course, the challenge then became to tackle the consistency of analysis, second-order arithmetic, which deals with real numbers and functions.
That was, and still is, a much harder nut to crack. Gensen himself made some initial attempts, and later Schutt and Takuti developed powerful techniques using infinitary logic.
But proving the consistency of full second-order arithmetic is still an open problem, right?
It is, although significant progress has been made on subsystems, showing the consistency of certain important fragments of analysis.
So the quest for consistency continues.
It does. and it drives research into ever more sophisticated proof-theoretic methods.
But while that quest goes on, Kenson's other great contributions, natural deduction and sequent calculus, have also continued to develop.
Absolutely. Prewitz's work in the 1960s really revitalized natural deduction, providing rigorous proofs of normalization and strong normalization.
And then there's the incredible Curry-Howard correspondence, which links proofs to programs, logic to computation.
That's a truly mind-blowing connection, revealing a deep unity between these seemingly disparate fields.
And sequent calculus has also seen remarkable developments, with things like invertible rules, making it more suitable for automated proof search.
And the G3 calculi, which offer even finer control over the structure of proofs.
So proof theory, which started as this foundational quest for certainty, has branched out in all these fascinating directions.
It has. It's a vibrant field with deep connections to computer science, logic, and the philosophy of mathematics.
And even though it might not be on every mathematician's desk just yet, the rise of computerized proof assistants and automated theorem provers could change that.
It could indeed. Proof theory is becoming more and more relevant to the practice of mathematics, especially as computers play a larger role.
So for our listeners, the philosophers among them, think about this. Proof theory has shown us the inherent limitations of formal systems, but it's also given us these incredibly powerful tools for analyzing and understanding the structure of proof itself. What does this tell us about the nature of knowledge, about the limits of what we can know and prove?
And what about the relationship between constructive and classical reasoning? Does the Curry-Howard correspondence suggest a deeper connection between the world of ideas and the world of computation?
These are big questions, deep questions, and proof theory offers us a framework for grappling with them.
It does indeed, and it's a framework that continues to evolve, revealing new insights and connections.
So keep exploring, keep questioning, keep pushing the boundaries of what you think you know. That's what proof theory is all about.
It's a journey into the very heart of reason itself, and it's a journey that never truly ends.
Well said. Thank you for joining us on this deep dive into proof theory. Until next time.